from the Department of Algebra, my colleague in the Department of Algebra in Caroline, Sebastian Opper, who will speak about the integration of Hochschild cohomology and derived Picard groups.
Yeah, thank you for the introduction and for inviting me to give a talk here. I hope, does it work with the microphone and my levels of my voice? Okay. Yeah, so thanks for the talk, Julius, as a preparation for this. There are some groups which I will roughly explain what they are. And the idea is that there's a sort of generalization of this classical relationship between Lie groups and Lie algebras, between Hochschild cohomology, which is a Lie algebra, as we've seen, even graded, and then things which are not quite Lie groups. But sort of the idea is that there's something in the background with the same spirit. And this is what I will talk about. And I was told that not everyone is super familiar with derived categories and triangulated categories. So I want to take the time and talk a bit about those and some motivation and stuff, so we're on the same page. So this will be the first thing, and then I try to motivate this a little bit. Okay, so I start with some overview on triangulated categories, and then a special part, a special kind of example of those called derived categories. Yeah, and I hope I'm not repeating too much, but I hope I also give a bit of an idea what these are in case you haven't seen them. So a kind of very general framework you might start with is if you have an arbitrary category, our assumption so far, then you can of course study always things like isomorphism classes. Of objects in C. And a sort of famous example where people thought about this is if C is a category of topological spaces, in which case isomorphism classes are nothing else but homeomorphism classes. So this goes back to the question, can you deform spaces and see if they're the same? And can you find invariants that test this and so on? And kind of turned out this is too complicated. And I don't know the exact theorem, but there's something like this. A certain kind of problem is undecidable and so forth. So there's a limit of how much you can understand this. So the idea is, well, okay, if this is a bit too much to ask for, can you widen this notion of equivalence or what it means to be isomorphic a little bit? So what I just said, so this is this kind of idea to classify objects in a category, even things like spaces. This is too much to ask for, and this is too difficult. Or, as I said, sometimes even impossible in a certain sense. So then the usual way we do things in mathematics, we try to do the next best thing, which still gives us some information. And the idea is that you understand objects, for example, topological spaces, up to some weaker notion of equivalence. And there's sort of historically two candidates that people have been looked at. So one is, for example, you can ask when are two topological spaces, X and Y, homotopy equivalent. So they're not homeomorphic, but you can deform them one into each other. And then you can go even weaker than that, and you can ask if two spaces like this, and this is sort of the motivation also for the name, weakly homotopy equivalent. Now, just for the sake of completeness, that just means is, so there exists a map from X to Y, which is continuous, so a morphism top, such that the induced maps on the homotopy groups between the two, this is an isomorphism, roughly speaking. So I guess okay, I don't know, I guess this is no, but for I equals 1, this is the fundamental group, and then you have phi analogs of this. This is what's called a weak homotopy equivalence. And that is sort of the starting point for a lot of modern algebraic topology. Then you're on this well. If you want to retain a bit more structure, because you started with the category, and then of course you lose a lot of information about morphisms if you just talk about isomorphism classes, what you want to do is to kind of be able to regard these types of equivalences, which, for example, in this case, they boil down to certain maps. You want to make these maps invertible, and therefore turn a category into another category where these things are actually isomorphisms. So, let's see here. So the general procedure would be so you take the category C as above, and then you take class W of morphisms in C. And I mean, in this kind of generality, you don't need to assume anything on them. For example, maybe in reasonable cases, you want this to contain all isomorphisms, like all homeomorphisms, but maybe some weaker things like all weak homotopy equivalences. And then there's a categorical construction you can do, which is very much the analog, although more complicated than the localization of a ring at some elements, is the localization of this category along this class of morphisms. So this, so you get a localization. Often denoted by this. And this formally inverts all these morphisms of W. And it does this in a universal way. And so this has some universal property traceable in terms of functors, which I'm not going to repeat. But it's kind of similar to what you would expect, similar to the localization of a ring. Okay, and that is like the whole topic of when these exist and how you compute them and so forth, which I'm not going to get into. But just to emphasize, we'll give you 2 examples. So one is basically what I said before, just to write this down. So you, for example, can choose, well, this could be all homotopy equivalences. Or you could choose, well, this could be all weak homotopy equivalences. And then if you, I'm leaving out maybe some details of what you actually want to do. What you would derive is if you do this, you get the homotopy category of spaces. In modern sense, probably more likely to mean this than this. And if you do sort of some extra steps before you do this kind of localization procedure, again, I'm not going to get into this, then you get what people would call the homotopy category of spectra, which is then sort of the object in algebraic topology, or at least a lot of this. But okay, like an example maybe, so this is maybe from the topological side, which I think motivated most of these kind of things. And then from the algebraic side, which is also closer to what we just talked about, the second example would be, well, you could also take C, could be the category of chain or co-chain complexes. Of R modules, whereas your ring of choice. And then W, a common choice that people would do, is the class of all quasi-isomorphisms. What are these? So these are all maps of chain complexes. Let's write this. Which induce, similar to here, but now isomorphisms on all cohomology groups. I now in Z. Okay, but so this is kind of very similarly modeled like this. And what you then get is what is called the derived category. So with this choice of C and the things you want to invert, this is usually denoted by dr, and this is called the derived category. Okay. So all of this kind of stuff comes from the same procedure. You have something which is a bit more general than isomorphisms, like normal isomorphisms of chain complexes are quasi-isomorphisms, normal homeomorphisms are weak homotopy equivalences, and you want to invert those. And then, for example, if you do this here, one reason to look at this is because this is the natural setting to do a lot of things, like homological algebra, derived functors. The same way that these kind of categories here are the natural way to do things like singular cohomology or homotopy groups and like all sorts of things. Setting for, in general, homological algebra. For example, this could mean, cohomology. It could also mean Hochschild cohomology. Julius mentioned this is a derived functor. And derived functors also sit in this kind of frameworks. Derived functors, don't know what else, other stuff. Okay. So they kind of arrive from a similar formalism. What they do have in common, which talk about in a second, is they have a bit of more extra structure. They're not just a category, but they remember something very vital from the categories they were constructed from. But maybe I want to draw a picture slightly to give you an idea what we're talking about. Right functors. So there's a generalization of this. So R in this case was a ring. But it can be something more general, where you also have a derived category and like very similar theory. Where R is a so-called DG category, or something even more general called an A infinity category. And it's not important what these things are. A DG category with one object would be called the DG algebra. And using this formalism that we had before, that associativity is something like you have an M, a multiplication map, so that the composition product with itself is 0. In this case, you have the M in the Hochschild space, but it doesn't only have a multiplication with 2 inputs and 1 output, but it has a bunch of multiplication maps with several inputs and 1 output. So it's a bit more complicated and is a more general form of associativity. They're also called in a certain sense homotopy associative algebras. So you kind of make strict associativity a bit weaker, and then yes, also coherences. Any case, so like this is a generalization of a ring, a very vast generalization of a ring. And in fact, it's so general that you sort of from different areas, you can all get into the same setting. So we have this kind of objects that I haven't defined. But now you can go from representation theory. So you, for example, representation theory. So for example, you could have a ring R. And then you can take chain complexes. This would be an example of a DG category, whatever this is. But you can also come from things like algebraic geometry. So you would have something like scheme, for those here who know what this is, scheme or variety. So 0 sets of polynomials, and then you can take something called X modules. Again, you have to be a bit careful, but then you also can get a DG category, something out of this.
Very basic.
Yeah.
So if you have a functor and you localize, do you always get a functor on the localized category?
If this functor inverts these things. So if you have a functor out of C into D, so that it sends every morphism in W to an isomorphism, then you get a functor. And it's exactly the universal property that you get the unique induced functor, and that sort of specifies the localization up to equivalence.
Following from that, so what is it if you have more structure on the category, like a monoidal category or a braided monoidal category? Can you say localized one is also monoidal or braided?
I think I'm unfortunately not qualified to answer that. There's the kind of thing I haven't thought about. Possible. I mean, yeah. No, I have no idea. Yeah. Yeah, when you say, for example, Hopf algebras, this is unfortunately connected to some of the things like the Hochschild complex and so forth. It's like a DG Hopf algebra in a sense, but yeah, I don't, yeah, unfortunately outside of my area of expertise. So like we can go from rep theory, which is sort of concerned with rings and modules and so forth. We can go from one sort of algebraic form of geometry. We can also come from a different place, which would be called symplectic geometry. This is concerned with certain nice even dimensional manifolds called symplectic manifolds. And then they have certain nice submanifolds called Lagrangians. And if you want to understand the whole complicated intersection theory of these, which is sort of very rigid, then you can bundle all of this up together into something called the Fukaya category. And while we're sort of naturally from this place, we always land in the G categories, which are a bit more rigid and nicer, although in terms of theory, they're the same. if you come from here, you don't get a DG category usually, but in actual infinity category. So this is why I included it. But so you can sort of start from different areas, and you have one type of object which unites all of them in a certain sense, which also allows you to maybe compare categories coming from here with categories coming from here in the same way. And if you do this with this side and this side, this is what people do, and it's what's called homological mirror symmetry and so forth. But if you if you go from here, I don't know, it gets, I guess, increasingly invisible. So if you go from here, you can go to the derived category. Yeah, and then you get something which is in the land of so-called triangulated categories. And if you come from this, I didn't write down what this is. Let's just call this homotopy category of spaces. And this here, homotopy category of spectra, like this. And you can't really do this. This will not be triangulated. But if you take this, you can also, oh yeah, I should have done this on a different blackboard. So even you have topology in here as well. So this kind of is a framework which is very, very general and has connections, like is a language which incorporates a bunch of different areas. So this is why I would say these are very attractive to look at. Okay. So that's this. Okay, so I mean, I won't go much into detail, but I want to say something what is a triangulated category a little bit. So the triangulated category. What is this? This is an additive category. So we have as Hom spaces, these are abelian groups. And then you have an important extra structure. This is where this triangulated part comes from. It's called this T, but it comes with a choice of so-called distinguished triangles. And there's different ways to write them. Maybe this one will, the triangle part, less apparent. But it's sort of sequences. This kind. So what does a sequence mean? So F, G, and H, these are morphisms in T. And the sigma here, that comes on the end, this can be an automorphism or more generally an autoequivalence of T. Also called the suspension or the shift functor, depending on the context. The reason this is called triangle, you can sort of, if you forget the shift part, you kind of wrap it up. So you would have something like F, Y, Z, and then here, it's up to forgetting this kind of shift bit, you have this kind of triangle. Yeah, and so you have a collection of these triangles, which are called distinguished, and then of course they have to satisfy a bunch of conditions, which I'm not going to repeat. Okay, maybe I give two examples in these kind of sort of familiar things that give you distinguished triangles. These are not all of them, but common examples or the motivation for them. So if you start again from the topological side, then you have fiber sequences. So what do I mean by this? So you have a fiber bundle. Or if you want, and B is a manifold, just a vector bundle, for example. And then in there, here you have the fiber over any point that you choose. And sort of it doesn't matter up to homotopy because this is a fiber bundle, which point you choose. So you have the fiber F, which you then embed into E. Over some point of your choice. Okay. And then, for example, what you would get in this homotopy category of spectra is you get a distinguished triangle basically coming from there. So you have F, then let's give this a name, I into E, and then a projection onto the fiber bundle. And then a sigma here is something very specific, which is called a suspension, hence the general name. This is just a topological construction. So that's one example. So you can think of these maybe in a topological setting as these distinguished triangles as sort of nice generalizations of a fiber sequence. We have a fiber bundle and then a fiber as the inclusion. Very similar to this in algebra would be short exact sequences, where you have a map and then a fiber over zero, which is the kernel on the other hand. That would be the second example in this derived category would be, so if you take NR as a ring, and then you have a short exact sequence of chain complexes, or as a special case when these are just modules, this gives you also a short exact sequence of chain complexes. Or chain complexes, or if you want just modules. Are modules, then you go also there, so like this is I and this is P. Then you also get a distinguished triangle. And here, this kind of suspension functor is just a shift. So where you shift your complex by one. So here's also a generalization of short cycle sequences in a sense. And yeah, that's maybe all I wanted. How you get? Do you get this one? What? Yeah. Yeah. So there's what's the name of this lemma? What you get? But there's a certain map you can construct, and this map is sort of technically only defined if you own complexes up to sort of homotopy and stuff. But then as a morphism in the derived category, it's actually well defined. So it's just the things like the snake lemma comes in case for those people who know this. So there's a sort of construction that you use to get this one. I can't write this down so quickly. So it's like, yeah, you do some diagram chasing, and then if you choose something, then yeah, it depends on the choice, but not in this category. This also has to do with, this has a different descriptions where you take something like intermediate instead of quasi-isomorphisms, you have something like homotopy equivalence. of complexes, and then you go further. Anyway, but yeah, so this is not so straightforward how you construct this. But these maps here, at least, I mean, the same way in the sense. These maps here are this, and then this is more or less determined. Okay. So yeah. And now what we want to do is, so we have triangulated categories, and now we want to study their symmetries. Same way we can study automorphism groups of groups or whatever, we can study sort of automorphism groups of these categories. Or autoequivalence groups, that's more appropriate. And this is where the derived Picard group comes in. Now I will. Sort of the main object I want to talk about in this talk are then eventually symmetries of derived categories. By this I mean those which kind of respect this extra structure, which are compatible with triangulated structure. So for example, if I apply like an element, a symmetry to a triangle, I want to get a distinguished triangle. Compatible with triangulated. Okay. And then, so derived Picard groups are sort of exactly this, but we sort of do remember that we don't just have a triangulated category, but this arose from something with a bit more structure in the form of the G category. Oops. So in a sense, without maybe defining them. I mean, I can also do this, but I don't know how helpful this is, especially if you haven't seen derived categories before. So these are not things of a triangulated category, but of a DG category, or an A infinity category. And then in a sense, things which see a bit of more of the structure we started with, you could say the enhanced versions. So without giving you the definition, I want to say, well, what's the comparison at least? So there's a connection between these two. So there's a group homomorphism. So if R is a ring or EDG category or whatever, so this is the derived Picard group. Then you get a map into what basically I said here, symmetries. So where you have an equivalence here. Where this is compatible with a triangulated structure plus something else, like it needs to preserve coproducts, but let's forget that. There's a sort of continuous version of this. And this map is not always an isomorphism, and it's very tricky to generally say how they actually exactly compare. But sort of what turned out over the study of, topology, but also in algebra, if you just work with the triangulated category, you're often screwed. And a lot of constructions you naturally want to do to produce new categories don't work in this generality, but they work really well in this generality. So if you take into account this bit of extra structure, then everything is better behaved, and you can do a lot of constructions. This is the reason why you usually focus more on these nowadays in many cases, and this is also why it's a good reason to look at this, which is sort of the replacement for that. But there's a relationship, and sort of if I told you the derived category is an extra structure, this is a very reasonable thing to look at. And then from that sort of historical perspective, this as well. T-structure? Sorry, what do you mean? Where's the T-structure, or what is it? Sorry. No. Yeah, it's more the idea that you can take C, but then you don't want to, let's say, you want to do homotopy theory on C. So if you go to the localization itself, you just forget too much structure. If you do localization, you're here. So you want sort of C, but in a kind of less rigid way. And there's sort of different models for this. I don't know, it's like there's like model categories and all this stuff. So they give you all the same localization, same homotopy theory. So there's different approaches to like category of spectra and all of this. But there you always encompass like some more structure. But it's not the derived category plus something. It's more like you start with something which can produce the same derived category, but you just start with more structure to begin with. It's more like this. T structure would be, there you can kind of truncate. Like if you have cohomology, you can sort of separate things in two sides. That's more, that's more on this. Okay. So I decided to not like give you actually the definition. This can also be done in bimodules and so forth. In derived functors, but I don't think it's very appropriate if I first just told you what a derived category is. But you can think of this as the appropriate replacement for symmetries of the derived category. Maybe as a slogan, sort of. It's roughly speaking, group of have to be very careful what this means, but I would maybe, for the purpose of this talk, say it like that. Okay. And then I just maybe give you some examples, and this might be relevant to different people who have seen different stuff. So A is a commutative algebra. Then you could go look at the derived Picard group here. And then you have a relationship between this and things which are familiar for people who know some algebraic geometry. So you have a thing which is called a Picard group of the spectrum. So this would be an affine scheme. And then you also have the automorphisms of this scheme. sorry, this is automorphism of spec A for those people on the right. And then you always have in there the shift functor. So which sigma here, or actually the shift on complexes, there's always is something in the derived Picard group. So this is how if you get this part for free, this is more interesting. So for those people who know what a Picard group is, you can look at this as a sort of derived generalization of this. So it's bigger in general, it contains this. In some specific cases, actually exactly that. In general, if this is not an affine scheme, but something more complicated, it will be just a subset of this. And then, yeah, I want to sort of give you a very small example where I changed something slightly, and the effect on this derived Picard group is very big. And then we want to talk a bit later how you can discover why. So you can look at the derived Picard group of just the dual numbers, right? And just to emphasize, I want this now not to be degree 0, which normally, but I could look at this as a graded algebra where I have this, for example, degree 1. Oh, sorry, no, maybe I want, I want this to be degree 0. And then we're actually in this kind of setting, right? So we know what this will be. And in this case, it's something very simple. We just have Z and then K star. So all the non-zero elements of K. Okay, but if I change this degree to anything other than, so like, now, for example, degree 1, which is a very special case, out of the sudden, this derived Picard group explodes. So you have this, but then you also have, I did like this, the continuous automorphism group of the power series ring, which is very big. And I use a different variable because this now is in degree 0. And as a set, not as a group, but as a set, for example, to see that this is actually kind of humongous as well, you can get an identification between this and, well, everything you have 1 plus anything which has a power of t at least. So in particular, this is not only finite dimensional or anything. So in particular, this is not something like a Lie group, right? It's just too big. The reason I say this because from now on, I want to pretend it is, regardless of the fact that it's definitely not. Yeah. And next, I want to record a little bit the relationship between Lie groups and Lie algebras, and I want to motivate what I'm sort of do right at the end. I just basically state one theorem. Yeah, are there other questions, by the way? So the question is, okay, if you believe me or not that these groups are interesting because they're sort of approximations to this, or maybe the even more interesting variant because we take into account this higher structure enhancement, the G category it came from. Then the question is, how do you compute this? So, the idea is also to do this as general as possible because I don't have it here, but we had this sort of common setting of the G categories. So if I can do this reasonably well, or have at least some good strategies to do this in this kind of general setting, I can sort of get information about lots of different objects from lots of different areas. So then what we're going to do is, okay, even though this is clearly not a Lie group, we're just going to pretend it is. There for Lie groups, there's a lot of nice classical theory, and maybe we can be guided by some intuition to do something. So what will we do? So in general, so that's sort of the guiding line, and now I just start in general. So if G is a Lie group, then I can always look at the connected component of the neutral element. So I will call this, bless you, G circle. So some neutral component, identity component, whatever you want to call it. And then when I do this, I can also get like canonical short exact sequence. So where this is just the inclusion, and this is always a normal subgroup, and then I can just take the quotient here. And then this sort of by definition will be discrete. And in general, there's little hope because, like, I mean, if this is a discrete group, this would be trivial. And then this is just any group you have. So it's kind of impossible to have something where the possible outcome is basically any group. So I would argue that to find some general strategy to compute this for an arbitrary DG category is sort of hopeless. But what you can try is to maybe focus in on this. So you split the problem into this, and sort of this is how I came with this. In certain categories and circumstances, I wanted to compute this, and I had a very good idea about this because my DG category came from geometry and so forth. But this was the difficult part. And what I want to say is, how can you compute this? And this is where Lie theory comes in, because this can be computed with the Lie algebra, as the classical theory says. Okay, so the classical relationship is we can understand this, or at least, there's a lot of ifs and so forth, but in the most general sense, via the Lie algebra of G, which, just to recall this quickly, is just a tangent space at the neutral element. Tangent space at E, okay? And the way to do this, to relate these two things, is via something which is called the exponential. So and this is a map which goes, I will explain what this means, from some U, which lies inside this Lie algebra of G, and this is a neighborhood of 0. So this is a finite dimensional vector space. So I can talk, well, yeah, okay. So in this case where we're Lie groups, we're over R, right? So our field is the real numbers, and then we can talk about neighborhoods here. So this will be a neighborhood of 0. G, which is R to the dimension of G, right? So this is a map, and it uses vector fields and so on. So that's why the title was integration, because what happens here, you can identify this with certain vector fields, and then your flow for vector fields, and then you integrate them literally. And you get a map from the Lie algebra into the Lie group. And this has some nice properties, because not only get you sort of as a set something in the image, so you can kind of sort of explore your Lie group via your Lie algebra, but you also can recover the group structure here with something called the Baker-Campbell-Hausdorff formula. I know that some people do stuff with Lie algebras here, so I'm hoping I'm not saying something everyone knows anyway. My apologies for this. So, the point I want to get is that this exponential group allows you to say something about this identity component without knowing the identity component. So this is not just a map, but it also satisfies a very important formula. So maybe the question is, if you have, let's say, two element x and y, you take the exponential, and then you have the multiplication of the Lie group, then if you're close enough to 0, you can write this as the exponential of something where this looks roughly like this. So you have the addition, and then you form the addition by something which comes from the Lie bracket. So you will have terms like this, for example, and so forth. And this is just, well, it has some denominators as well, but in particular, this consists only of iterated Lie brackets, where you just nest this more and more. And this is a series, so you also need some sense of convergence and so forth. This is why you need everything to be small. But this is the Baker-Campbell-Hausdorff product. And then some people, because the actual formula I kind of started writing down was due to Dinkin, also put his name rightfully in there. But a lot of people also don't. So this is a formula. And then what you get is that U, together with this product, actually becomes a group. And again, this only depends on a Lie bracket. So if you understand the Lie bracket and sort of what convergence means, this is a group which you can compute, even though it might be complicated. But the exponential here, which goes into here, this then becomes a group homomorphism, right? So that when you also know what the kernel does, you can compute the image, right? So you get an isomorphism group, kernel of the exponential onto the image of the exponential. And then maybe as a remark, so this is not always injective. So the kernel is isomorphic to the fundamental group of your Lie group. Insects. So this is isomorphic to the fundamental group of G. So this is why, I mean, often in the literature you find there's something simply connected, blah, blah, blah. So this is 0 and this is injective. The exponential is also surjective if G is compact. Surjective onto the identity component. But the most general setting, which is kind of useful because in the algebraic world, we don't know what compact is supposed to mean, or the fundamental group and so forth. It's better to just not assume this, being this more general thing, and then sort of we need to take care of things like the kernel and so forth. Okay, add an example. Okay, maybe I'll write this down very quickly. So, for example, you have an idea, this exponential group. I mean, the normal exponential map is an example, of course, of this. So if you take the general linear group, and then the Lie algebra of this, it's just all the square matrices. With the usual commutator bracket, then the exponential of, let's say, a matrix A is just the matrix exponential. So okay, and then again, you need some conversions for this. So yeah, and then the Baker-Campbell-Hausdorff formula, if the Lie bracket vanishes, gives you the familiar thing, exponential of the sum is the product of the exponential. So I'm going to skip that bit. Okay, but so this is a formula, and what we needed was convergence in a certain sense. And to define this in a real sense, we needed some integration, some vector fields and all of this stuff. And what we now want to do is we wanted here to have Hochschild cohomology, and this should be the derived Picard group, where we don't have vector fields or kind of convergence a priori. And so just quickly, if I have 5 minutes, is that okay? I write down the definition which uses this composition product you just mentioned. And then one theorem, and then we're done. Okay, this was not so smart. Anyway. The idea is now we want to mimic all of this. Well, this is not how you write this, right? But we want to mimic this relationship for G equals to the derived Picard group of something, and then sort of the Lie algebra of G roughly speaking. But this is not a Lie group. So, and this, for example, as we've seen, can be okay, we haven't seen it, but the point is this can be infinite dimensional and very big. So there's no finite dimensionality, vector fields, nothing. And I maybe just write down the definition first, and then we can discuss this a little bit. Yeah. So, as I said, so we have the problem that we don't have any integration or anything. So we can't go to geometry, but we have this formula. And if you're very naive, you can try to mimic this formula and see if it has a good property. The question is, what is this multiplication here, right? Because this came from the group, but we don't really know the groups. It's not really what we want to do. The idea is, what turns out to be a good thing is you take the composition product, which is not associative, but it does a trick. So if you take some something in the Hochschild complex of R, and this also exists in very general settings, DG, cat, and so forth. Then what you want to do, assuming that the characteristic of your field is 0, of course, can define this. Define this in a similar way. Take H here, where this is the n-fold composition product, but this is not associative. So you need to say what this actually means. So n is by definition so you bracket it from this way, sort of from the left. And then this, again, by definition, is the identity, which in this grading that we had would be an element of degree 1. Yeah. Oh, sorry, yes, yeah. No, I figured because of the star, this will look very simple. Bad choice of notation. So this is not an associative product, and as you've seen, it's like defined by composing functions into each other. So it's actually very difficult to compute if you would just do this with a general thing. But it does the trick, and like the proof is actually not easy, and I haven't really shown you what derived Picard groups are. So there's a lot of details you have to take care of. But also the question is, what does convergence mean? Because this is still an infinite product. So unless this kind of vanishes, which it almost never does, so this never is sort of 0 after finitely many steps. What does convergence mean? So we need some condition, and you can define a topology here by some filtration. Try just quickly. Okay, maybe it's not so important then. Okay, maybe I just. So there's a filtration. Which is descending. Write this down. Where this is, so you had this Hochschild complex that was roughly defined by doing. So if you take functions and then you take a tensor product, like n inputs, and then here. The only thing you change now is you don't start at 0, but you only allow functions which have at least a certain number of inputs, namely I. So this gives you a descending filtration of the Hochschild complex. And then this, because it's complete and so forth, this gives you a topology. So this becomes a complete normed vector space. So this induces a topology on on CR, but it also induces this kind of descends to cohomology, as you can show, and also induces then filtration and topology on Hochschild cohomology. Okay. And then what we define as what our neighborhood will be, U, we will be, for some reason, which is maybe not obvious now, the second filtration step, where this is HH1. And I can also explain, if you're interested, why this is only one and not the Hochschild, not the complete Hochschild cohomology. This is exactly what you would expect. It's not a defect. But then this is really the last thing I write, the theorem. What you then prove is is very general, PG category. In the category, characteristic of the field should be 0. Then exists a group homomorphism from this choice of U here into the derived Picard group. And sorry, when I say group is, if you here, you can also define this Baker-Campbell-Hausdorff product in the same way, and this only uses the Lie algebra structure. So, as Julia said, this is called the Gerstenhaber bracket. And you can also say things about what the kernel sort of is roughly and so forth. But this can be very big, and then I don't know if you're interested. So like there was this example of this very massive derived Picard group that just because I changed the degree of the dual numbers. And this comes from this part. So we can sort of see this in action. In this very specific grading, sorry. Very specific grading. This had degree 1. This was the case where kind of this exploded and we had this continuous automorphism group. Then this U becomes the positive part of the Witt algebra, the completed version. Positive portion of the completed Witt algebra. So that's those who don't know, this is product over such things where your Lie bracket is the only continuous one where you have this rule. So this is like the Witt algebra, just you don't have the negative part. And if you integrate this stuff, you get this continuous automorphism group of the power series ring out of the sudden. But the idea is if you really want to, in cases where you had a sequence and I understand this and you want to understand this kernel again, it was very tricky to come up with the formulas because you actually in this, and then this can be described by certain complicated functors. And I couldn't guess the formulas, and the reason is because you have this thing out of the sudden coming up in these examples. And if you try to write down the Baker-Campbell-Hausdorff product for this, you can sort of see it gets very complicated. Yeah, so that's sort of the idea. So it's very similar to like Lie theory, just in a very different setting. Yeah, sorry for the overtime.
Okay, so do we have questions from the audience?
Yeah, sure.
Have something called this in C-star algebra world, and I'm just wondering
Yeah,
how
it's
similar.
probably very similar. So what you do is, so you take, so you're in now the derived category of bimodules over this. So yes, technically this. And then because this is not symmetric monoidal, but you have basically it's still the notion of a Picard group where you say, okay, like both tensor products are the tensor unit. So so that there exists some Y such that, well, in the tensor product is this derived tensor product. R as a bimodule. So it's just, yeah, the invertible elements in a sense. And I'm assuming this is maybe similar for C-star algebras.
Yeah.
Yeah, okay, yeah. Yeah, in a sense, exactly, yeah. But yeah, I didn't know. I thought some people don't know about derived, so I didn't kind of leave it out. It's not a complicated definition, but yeah, I wasn't sure if that would be helpful or not. Yeah. But yes, I mean, this is not the definition I actually use because like you might wonder, well, if I do the exponential here, I don't get a bimodule, but there's an alternative definition which used so-called A infinity functors, and then this is sort of the definition using, but yeah. Anyway.
So how does the norm on the vector space relate to the product? I mean, I'm looking for some sort of submultiplicativity
Yeah,
so that it's
so
clear.
the idea is that these are the like shrinking neighborhoods of zero. And then you have this sort of, well, norm with like a discrete set of values where you say, okay, something like the norm of something is 2 to the power minus I if the smallest thing where this sits inside is like this one. So this is kind of how do you get the norm.
And a different question for these Picard groups is, I mean, you're talking about Lie groups. Is there some notion of simplicity, semi-simplicity?
No idea in this setting. I mean, to be honest, I think like this is sort of a truncated version of, I guess, how one should really do this. Like you might, for example, wonder why. So yeah, the answer is I don't know, but I think it's also not sort of the right setting. You might wonder why there's only HH1. And what you should actually think of them as sort of spaces, like the same way like a Lie group is a space, right? But like in a sort of homotopic sense, sort of simplicial sets and so forth. And then you have homotopy groups of those and stuff. And I don't know what semi-simplicity in those kind of realms should mean really. So yeah, I'm not sure. I think, can you remind me what our theorem says? I don't know.
Get some possibly dimensional
group
and responding algebras, and you have the more nice notions of the exponents.
Yeah, no idea. I think, yeah. Yes, it's the other problem is sort of that. Yeah, I can only sort of see parts with the exponential. Like I have to really have a neighborhood, and I don't know how to deal yet with the. Yeah, well, you kind of should shift the. I guess normally how the proof works, you kind of shift this neighborhood around your Lie group, and then this is how you can cover everything, right? And I'm not sure exactly what the counterpart with this is, and to sort of. Yeah, so the answer, yeah.
I have also a question, even though I'm not sure if it's very meaningful. So for these Picard groups here, so those correspond to symmetries of your category that are kind of nice behaving towards these triangles, right? So
Yeah, in
if
particular,
you
yeah.
if you change now your choice of triangles,
Yeah.
does this have some impact on the corresponding Lie algebra that you get? So can I somehow see this on the local level?
Yeah, so the Hochschild cohomology, in a sense, if I'm not mistaken, is really invariant of sort of the DG category and not the triangulate category. So I think you could have sort of, not sure if there are examples, sort of different rings of categories which give you the same triangulated category, and yet the Hochschild cohomologies might not be the same. And sort of the triangulated structure comes once you have chosen this DG category. So that's not a choice anymore. There's like a canonical way to get this. So I can't really choose the triangulated structure and then get Hochschild cohomology. I need to start with something which has more structure, but then the triangulated structure is already determined. So they're not quite as independent.
Sure, but yeah, like what I want to understand is, so what does this mean on the local level, like on the U here, on the connected component of the identity?
Yeah. So this U is very dependent on this sort of choice here as well. I'm not sure if this answers your question. There's a sort of way that you can have different choices here, which give you the same triangulated category, and also like they're equivalent in a higher sense. So even the derived Picard groups are the same, but this neighborhood here will change. Mm-hmm. And you can have better choices where this neighborhood is sort of very large and gives you a lot of information. You can have very bad choices where this neighborhood, I mean, there's extreme examples where in one case it's literally 0, and the other case is almost everything. So this really depends highly on this choice. I don't know if this answers.
So are there any other questions or from anyone who's online? No? Okay, it doesn't appear to be the case, so we'll thank Sebastian again. And so next week's talk, okay, it's Sana Spuja and Sven Raum, both from Potsdam, University of Potsdam. Brilliant. Hopefully see you next week.